sac221 problem number 3 involves some light passing from one transparent medium to another. It starts out in vacuum, where the index of refraction is equal to 1, and it's got a certain wavelength, passes into a transparent medium of glass whose index of refraction is 1.50. And they want the frequency of the light and use that value to determine the wavelength of the light in the glass. So over here we got lambda 1 is equal to 465 nanometers, but here lambda 2, we don't know what it is, and that's what they want to know. The thing is, whatever the frequency is in this region, that's the frequency over here, so we don't need any subscripts. I'll just call it F, and I get the same frequency for the light there. Now, first off, let's go ahead and get that frequency. We got the wave speed, the speed of any wave, and in this case, the speed of light, I use the symbol C to represent the speed of light, is the wavelength times the frequency. And hence I can solve for the frequency with the given information and the known value for the speed of light in vacuum as C over lambda. Let's divide both sides by lambda and then switch sides. And that's 3.00 times 10 to the 8th meters per second divided by that 465 times 10 to the minus 9th meters. That yields a frequency of 6.452 times 10 to the 14th. Let's see, meters cancel out. I got 1 over seconds, and 1 over seconds is hertz. So 6.452 times 10 to the 14th hertz. And again, I'm keeping one more sig fig than called for, this being an intermediate result. I'll keep one extra and round off at the very end. Now, by the definition of the index of refraction of glass, N2 is equal to the ratio of the speed of light in vacuum to the speed of light in the medium. I'll call that V2. V2 is the speed of light in the glass. And so V2 is C over N2, arrived at just by dividing both sides by N2. And that's 3.00 times 10 to the 8th meters per second, all divided by that 1.50 with no units. That's index of refraction, has no units whatsoever. Then in the glass, the expression speed of the wave is equal to the wavelength times the frequency still holds. It's true, but we got a different velocity and we're going to have a different wavelength since the frequency is the same. Solving that for the wavelength this time, V2 over F is, well, I better finish that one up. Get rid of the units there, and it's 2 by inspection, 2.0. I mean, you can do that one in your head. Times 10 to the 8th meters per second is the speed of the light in the glass. Now, I substitute that into this expression. And that's all being divided by the frequency, 6.452. hertz, which is 1 over seconds, canceling out the seconds, so we do get something in meters, and that turns out to be 310 times 10 to the minus 9th meters, or 310 nanometers, where that last digit is significant, as indicated by the fact that I put a decimal point after the value. So we get 310 nanometers for the wavelength of the light inside there. Outside it was 465. We see that the wavelength decreases. Crests become closer together, as they must if you imagine somebody at a given point in space. If the frequency is the same, you're going to have the same number of crests passing your position per second. And if the wave is going slower, then in order to have the same number of crests per second passing your point, your position, namely the frequency 6.452 times 10 to the 14th of them per second, in order for you to have the same number per second passing your position, they've got to be closer together if they're all going slower. So our result makes sense. And indeed, the wavelength of the light in the glass is 310 nanometers. That's our answer for